Welcome to this quiet space, a gentle sanctuary designed for rest and peaceful contemplation. Tonight, we will begin a slow and wondrous journey together, drifting among the stars on a current of ancient light. We will explore the silent stories written in the cosmos, tales of immense age and breathtaking beauty, allowing their gentle rhythm to guide your mind toward a deep and restorative sleep. Before our journey commences, I would love to hear where you are listening from this evening, or perhaps a simple reflection on your day. Your presence here is deeply appreciated, so please feel free to leave a comment below. And if you find solace in our time together, please support this channel with a like and a subscription, so that we may continue to share these moments of peace. Thank you so much. Now, find a comfortable position, let your body feel heavy and supported, and allow your breath to slow as we turn our mind's eye toward the heavens. The simple, profound act of looking up into the night sky is perhaps the oldest form of meditation humanity has ever known. A silent conversation with the infinite that requires no words, only a willingness to receive the ancient light that has traveled so far to greet you. Imagine for a moment a single particle of light, a photon, beginning its journey from a distant star thousands of years ago, a tiny, weightless messenger setting out across the unimaginable emptiness of space. This journey is governed by a fundamental constant of our universe, a cosmic speed limit that nothing with mass can ever break. The speed of light itself, it travels at a pace that feels instantaneous to us in our daily lives, a speed of approximately 299,792 kilometers per second, yet on the scale of the cosmos, this incredible velocity becomes a patient, crawling measure of distance and of time. Because of this finite speed, every star you see is not as it is right now, but as it was in the past. The light from a star 100 light-years away began its journey when your great-grandparents were young, carrying with it the image of a star that has since aged a century. The starlight that graces your vision tonight is an echo, a memory, a luminous ghost of a moment that has long since passed. And in this way, every glance toward the heavens is an act of time travel, a looking back into the deep history of the universe. This tiny messenger, the photon, is a marvel of existence, a fundamental quantum of light that possesses a strange and beautiful duality. It is a particle, a discrete packet of energy with no mass and no charge. Yet it also travels like a wave, an oscillating ripple in the electromagnetic field, dancing its way across the cosmos. It is both a thing and a motion, a traveler and the journey itself, a perfect embodiment of the universe's elegant complexity. Think of this single photon, born in the fiery heart of a star long ago, traveling in a perfectly straight line through the silent, cold vacuum, past swirling nebulae and wandering planets, on a trajectory aimed with impossible precision across trillions of kilometers of nothingness. For all those centuries, it has been utterly alone, an emissary from a distant sun, carrying a single, simple message. The image of its origin, and the destination of this ancient traveler is you. After its immense journey, this particle of light completes its cosmic pilgrimage in the most intimate of ways, by passing through the lens of your eye and coming to rest upon your retina. Here, in the delicate, light-sensitive cells at the back of your eye, a beautiful and final transformation occurs. The photon strikes a molecule called rhodopsin, a complex protein that has evolved over eons for this very purpose, to receive the light of the stars. The energy of that single, ancient photon causes the rhodopsin molecule to change its shape in an instant, triggering a cascade of chemical signals that become a tiny electrical impulse in your optic nerve. This whisper of electricity travels to your brain, where it is interpreted, understood, and felt as a point of light, a single star in the vast dark tapestry. A journey that spanned centuries and crossed the void of space finds its conclusion in a silent, microscopic chemical reaction within you. The star, in a very real sense, has reached out and touched your consciousness. Every star you see is the endpoint of countless such journeys, a shower of ancient light particles completing their pilgrimage, weaving the history of the universe directly into the fabric of your own perception, a silent, luminous conversation between the cosmos and your quiet, observing mind. This silent conversation with the past is a constant in our lives, an ever-present stream of messages from the cosmos, and the most immediate, the most powerful of these celestial greetings comes from our very own star, the Sun. While the light from distant stars speaks of ancient history and deep time, the light of our Sun tells a more recent story, a tale that is both epic in its scale and deeply personal in its warmth. We often think of it simply as the Sun, but in the grand cosmic catalogue, it has a more specific identity. It is a G-type main sequence star, a classification that astronomers sometimes call a yellow dwarf. This name, however, feels a little misleading, for there is nothing small or dim about the star that anchors our solar system. Its yellow-white glow is a sign of its stability, its calm and steady temperament, a star in the long and peaceful adulthood of its life, a comforting and reliable presence that has nurtured our planet for billions of years. Its light feels so immediate, so present, a constant companion to our days, yet even this familiar light carries within it a hidden story of an immense and ancient journey, not through the void between stars, but through the incredible density of the star itself. When a photon is born from a fusion reaction deep within the Sun's core, its path to freedom is not a straight one. The core of the Sun is a place of unimaginable pressure and temperature, a plasma so dense that our newly created particle of light can only travel a fraction of a millimeter before it is absorbed by a proton or an electron. It is then re-emitted moments later, but in a completely random direction, beginning a process that has been poetically described as a random walk. The photon staggers and zigzags its way through the stellar interior, being absorbed and re-emitted millions upon millions of times, its direction constantly changing, making almost no outward progress. A journey that would take just over 2 seconds at the speed of light in a straight line becomes a staggering odyssey that can last for tens of thousands or even hundreds of thousands of years. The light that warms your face today may have been born in the Sun's core before human civilization began, a truly ancient particle that has spent an eon trapped within the labyrinth of its own parent star. This long meandering dance through the Sun's interior is a profound illustration of the star's immense density and scale, a hidden age layered within the light we perceive as new each morning. But eventually, after its long imprisonment, the photon reaches the Sun's surface, the photosphere, and from here, its journey changes completely. It is finally free, released into the vacuum of space to travel unimpeded. This is the final, glorious sprint, a straight and true path across the 150 million kilometers that separate the Sun from our Earth. This part of the journey is swift, taking only about 8 minutes and 20 seconds to complete. So the warmth you feel on your skin, the light that allows the trees to grow and the oceans to shimmer, is a beautiful paradox of time. It is composed of photons that are, at once, over 100,000 years old and just over 8 minutes old. It is both an ancient artifact and a fresh message, delivered to us across the solar system, carrying with it the story of its long confinement and its final, radiant liberation. And the Sun's presence is felt not only through its light. Our star also breathes, exhaling a constant stream of charged particles known as the solar wind. This is not a wind in the earthly sense, but a flow of plasma that travels outwards through the entire solar system, a physical touch from our star that interacts with the magnetic fields of planets, creating the beautiful dancing lights of the aurorae on worlds like ours. This invisible stream is the Sun's constant, physical connection to us, a whisper that shapes the very environment of our planetary home, a reminder that we exist within the grand, dynamic atmosphere of our star, bathed in a light that is both timeless and immediate. That timeless, immediate light from our Sun does not end its journey when it reaches our world. Rather, it continues, scattering and reflecting in a celestial dance of borrowed illumination. And no object in our sky performs this dance with more grace and quiet majesty than our constant companion, the moon. We see it as a source of gentle silvery light, a beacon in the darkness, yet the moon produces no light of its own. It is a cosmic mirror, a silent, patient sphere of rock and dust that catches the brilliant rays of the distant sun and redirects them toward us, transforming their harsh, direct glare into a soft, ethereal glow. This gentle light has shaped the rhythms of life on Earth for eons, pulling on the tides, guiding nocturnal creatures, and inspiring a sense of wonder and peace in the human heart. But there is a beautiful deception in the moon's brilliance. As it hangs in the sky, a luminous pearl against black velvet, it appears to be a radiant white, yet, if you were to stand upon its surface, you would find yourself in a world of charcoal grey dust and dark rock. The moon is, in fact, incredibly dark, with a surface that, on average, has the same reflectivity as worn asphalt. It reflects only about 12% of the sunlight that strikes it. Its perceived brightness is an illusion born of contrast, a trick of our perception where its dimly lit surface is set against the perfect, ink-black emptiness of space. It is a profound reminder that what appears brilliant in one context is muted in another, and that even the most familiar sights can hold a hidden, deeper truth about the nature of light and shadow. This celestial play of reflected light becomes even more intricate and poetic when we consider the phenomenon known as earthshine. On a night when the moon is just a slender, silver crescent, you can sometimes see the rest of the lunar disk glowing with a faint, ghostly light. For centuries, this was a mystery, a soft luminescence that seemed to come from within the moon itself. But it is another form of borrowed light, a light that has travelled on a far more complex journey. It is sunlight that has first travelled to Earth, illuminating our bright, blue and white world of oceans and clouds. Our planet then reflects this sunlight back out into space, and some of it falls upon the dark, unlit portion of the moon's surface. This faint, twice-reflected light then travels from the moon back to our eyes, allowing us to see the full sphere. This beautiful effect, sometimes called the old moon in the new moon's arms, is a quiet conversation in light, a triangle of illumination connecting the sun, the earth, and the moon. It is the light of our own world, shining back at us from the face of our silent companion. And this companionship runs deeper than mere light. As you gaze upon the moon, you will always see the same familiar face, the same pattern of seas and craters that humanity has watched for its entire existence. This is no coincidence. It is the result of a process called tidal locking, a deep gravitational dance between our world and its satellite. Over billions of years, the Earth's powerful gravity has pulled on the moon, slowing its rotation until the time it takes to spin once on its axis is perfectly synchronized with the time it takes to orbit our planet. It is as if the Earth has reached out with a gentle invisible hand and asked the moon to always face it, creating a sense of constancy and familiarity in our ever-changing skies. This gravitational embrace is a quiet guardian, for the moon's steady presence also stabilizes our planet's axial tilt, preventing it from wobbling chaotically over geological time. It is this stability that gives us our predictable seasons, our reliable rhythm of summer and winter, spring and autumn, creating the stable climate that has been so crucial for the flourishing of life. The moon, in its silent, reflective way, is not just a beautiful sight, but a fundamental architect of the world we know, its borrowed light, a symbol of its deep and steadying influence. This gentle, steadying light has always served as more than just a nocturnal lamp. It has been a canvas for the human imagination, a dark and silent expanse that invited our ancestors not just to observe, but to dream. Looking up from the flickering light of a campfire into the profound stillness of the cosmos, we did what human minds are uniquely designed to do. We found patterns, we connected the dots, and we began to tell stories. The constellations are the oldest stories we have, whispered from generation to generation, a testament to our innate and enduring need to find meaning and order in a universe that can often feel vast and random. We see the heroic hunter Orion striding across the winter sky with his loyal dogs, or the great bear of Ursa Major circling the northern pole. But this act of celestial storytelling is built upon a grand and beautiful illusion. The stars that form these familiar patterns, which appear to us as close neighbours on a two-dimensional dome, are often separated by unimaginable distances in the true three-dimensional depth of space. In Orion's famous belt, for example, the leftmost star, Alnitak, is about 800 light-years from us, while the rightmost star, Mintaka, is over 900 light-years away. They appear to be aligned from our unique vantage point on Earth. A chance arrangement across the void, a temporary picture that would dissolve into a meaningless scatter of points if we could travel just a few light years in any direction. This realization does not diminish the beauty of the constellations, but rather adds a profound layer of perspective, reminding us that the patterns we see are a relationship between the cosmos and ourselves, a personal view of an infinitely deep and complex reality. Our ancestors used these patterns not just for myth, but for survival. The 12 constellations of the zodiac, for instance, hold a special significance because they lie along the ecliptic, the apparent path that the sun travels through the sky over the course of 1 year. As the Earth orbits the sun, our perspective shifts, and the sun appears to pass in front of a different constellation each month. This created a magnificent celestial calendar, a great cosmic clock that told ancient farmers when the seasons were turning, when to sow their seeds, and when to harvest their crops. The stars were their almanac, their map, and their guide. Yet even this grand clock has its own subtle, slow-moving drift. The Earth, as it spins, also has a slow wobble on its axis, a motion called precession that completes one full cycle every 26,000 years. This means that the celestial poles, the points in the sky that our axis points toward, are not fixed. Today, our North Star is Polaris, a bright and convenient marker in the sky. But for the ancient Egyptians building the Great Pyramids, the North Star was a different, fainter star in the constellation Draco named Thuban. Even the most seemingly permanent fixtures of our night sky are caught in a slow, majestic, and imperceptible waltz, a reminder that the universe is never static, but is always in a state of graceful, constant motion. The stories we tell about this moving canvas are as diverse as humanity itself. The pattern we know as the Big Dipper is seen in England as a plough, in ancient China as the celestial chariot of the emperor, and to the enslaved peoples of the American South, it was the drinking gourd, a symbol of freedom whose stars pointed the way north. Indigenous Australian cultures have some of the oldest astronomical traditions in the world, seeing in the dark lanes of the Milky Way not just the points of light, the shape of an emu in the sky, a story written in shadow and dust rather than in fire. The stars are a universal mirror, and in them, every culture has found a reflection of its own hopes, fears, and deepest beliefs, proving that the stories are not truly in the sky, but are carried within the human heart, projected outwards to find a home in the silent, listening dark. These stories we project onto the heavens, these myths of hunters and bears and celestial chariots, are a reflection of the human mind's search for meaning. But the stars themselves are telling their own, much older stories. We only need to learn how to listen, not with our ears, but with our eyes, for the tales are written in the subtle and beautiful language of light. When you first gaze upon the night sky, the stars may seem like a uniform scatter of brilliant white diamonds. But if you allow your eyes to relax and your focus to soften, you will begin to notice a delicate and varied palette of colours. Some stars glow with the deep, fiery red of a cooling ember, others with the gentle orange of a harvest moon, and still others with the fierce, electric blue-white of a lightning strike. These are not random decorative hues. They are profound diagnostic clues, a visible whisper that tells us about a star's innermost secrets, primarily its temperature. This symphony of stellar colour is a direct consequence of a star's surface heat, a cosmic thermometer that allows us to take the temperature of an object trillions of kilometres away. The coolest stars, with surface temperatures of perhaps only 3,000 degrees Celsius, emit most of their light in the red and infrared parts of the spectrum, giving them a ruby or garnet-like appearance. The hottest stars, by contrast, are truly immense furnaces, with surface temperatures soaring to 30,000 degrees Celsius, or even higher. These stars blaze with a brilliant blue or blue-white light, radiating immense amounts of high-energy ultraviolet radiation. Our own yellow-white sun sits comfortably in the middle of this range, a warm and steady G-type star. The physics behind this connection is an elegant principle known as black-body radiation, which describes how any dense, hot object will glow. Imagine a blacksmith heating a piece of iron in a forge. At first, it just feels hot, but as its temperature rises, it begins to glow, a dull red. As it gets hotter still, the colour shifts to a brighter orange, then to a brilliant yellow, and if the forge is hot enough, it will eventually become a dazzling white, and then even a blue-white. The color of the glow is a direct indicator of its temperature. Stars behave in precisely the same way. They are near-perfect black bodies, and the color of light they emit reveals their surface temperature with beautiful accuracy. This simple, powerful principle is one of the cornerstones of modern astronomy, allowing us to understand the nature of stars without ever leaving our world. To bring order to this diversity, astronomers developed a spectral classification system, a way of categorizing stars based on the information encoded in their light. This system is a simple sequence of letters: O, B, A, F, G, K, M. This sequence, often remembered by the poetic phrase, "Oh, be a fine girl, kiss me," arranges stars from the hottest and most massive, the brilliant blue O-type stars, all the way down to the coolest and dimmest, the gentle red M-type dwarfs. It is a language for reading the life stories of stars, each letter representing a different chapter in stellar evolution. To see this celestial palette for yourself, you need only look towards a familiar constellation like Orion. The top left star, Betelgeuse, is a magnificent red supergiant, an M-type star whose ruddy glow is the unmistakable sign of a star nearing the end of its life. Now, cast your eyes to the bottom right of the same constellation, to the star Rigel. It shines with a piercing, blue-white light, a brilliant B-type star, immensely hot, young, and powerful. In one small patch of the sky, you can see two stars at vastly different stages of their lives, their stories told in their opposing colors. You can find the cool orange of Arcturus, a K-type giant, or the brilliant, pure white of Sirius, an A-type star, the brightest star in our night sky. The heavens are a gallery of these stellar portraits, a silent symphony of temperature and time, each color a different note telling a story of unimaginable fire and immense patient age. This silent symphony of colored stars plays out across a stage of such immense size that our minds struggle to grasp it, a vast and quiet emptiness that separates each luminous note from the next. Gazing at the pinpoint of red light from Betelgeuse and the piercing blue of Rigel, we are left to wonder about the true distance that lies between them, and between them and us. How do we even begin to measure a void so profound? To do so, we needed a new kind of ruler, one immense enough for the cosmic scale, and we found it in the one thing that can cross that void: light itself. The light year is the result, a unit of measurement that is both poetic and practical, for it measures immense distance not in terms of length, but in terms of a journey. A light year is simply the distance that a particle of light travels in one full terrestrial year. Given light's incredible speed, this distance is almost incomprehensibly large. It is about 9.46 trillion kilometers. But dwelling on the number itself is less important than understanding the story it tells. It is a distance so great that the fastest thing in the universe needs an entire year to cross it. This unit transforms the static emptiness of space into a dynamic realm of time and travel, where every distance is also a history. To measure these distances to our nearest stellar neighbors, astronomers use a wonderfully intuitive method called parallax. You can experience the principle behind it right now. Simply hold one finger out at arm's length and close your left eye, noting where your finger appears against the distant background. Now, switch eyes, closing your right and opening your left. Your finger will appear to jump to a different position. That apparent shift is parallax. Astronomers do the very same thing, but on a cosmic scale. They use the Earth itself as a roving eyeball. They will photograph a nearby star against the backdrop of much more distant, seemingly fixed stars, and then they will wait 6 months for the Earth to travel to the other side of its orbit around the Sun. From this new vantage point, 150 million kilometers away from the first, they take another photograph. The nearby star will have appeared to shift its position ever so slightly against the distant background. By measuring the tiny angle of this shift, and knowing the diameter of Earth's orbit, they can use simple trigonometry to calculate the star's distance with remarkable precision. This method allows us to ground our cosmic map in real, measured distances, beginning with our closest neighbors. The very nearest star to our solar system, besides the Sun, is a small, faint red dwarf called Proxima Centauri. It is about 4.24 light-years away. This means the faint, reddish light we see from it tonight began its journey through space more than 4 years ago. It has been travelling through the void for the entire duration of a university degree or a presidential term. The star we see in our telescopes is not the star as it is tonight, but the star as it was 4.24 years in the past. Every star is a postcard from a different time, and this principle extends all the way to the edge of what we can see. Because the universe began with the Big Bang approximately 13.8 billion years ago, there is a fundamental limit to how far we can look. We can only see the light from objects that has had enough time to reach us since the universe began. This creates a cosmic horizon, a conceptual sphere around us that defines the boundary of the observable universe. The radius of this sphere is currently estimated to be about 46.5 billion light-years, a number larger than the age of the universe, because space itself has been expanding while the light has been travelling. This horizon is not a physical wall or an edge, but rather a horizon in time. Beyond it, there is surely more universe, more stars, and more galaxies, but their light has not yet had the billions of years required to complete its journey to us. The void of space is not truly empty, but is instead filled with these ancient, travelling stories, and the light year is the rule that turns the cosmos into a grand museum of time, where looking further out is always, and forever, looking further into the past. This cosmic museum, with its exhibits of light from every era of history, naturally leads the mind to a quiet and fundamental question. Where do these stories begin? Before a star can send its light on an ancient journey, it must first be born. And the birthplaces of stars are among the most serene and beautiful objects in the entire universe. The vast, ethereal, and majestic clouds of interstellar gas and dust that we call nebulae. From our distant perspective, they appear as soft, colourful smudges of light, like a watercolour painting spilled across the blackness of space. But if you could drift within one, you would find yourself in a realm of immense scale and profound quiet, a cold, dark, and mostly empty expanse of drifting hydrogen and helium atoms. These nebulae are the raw material of creation, the primordial reservoirs of matter left over from the Big Bang. Their composition is simple and elemental, made of about 75% hydrogen and 24% helium, with just a tiny fraction of other elements in the form of fine dust, like smoke. This is the cosmic clay from which new suns and new worlds are sculpted, and the sculptor is the most patient and persistent force in the universe. Gravity. For millions, and sometimes billions of years, these clouds can drift in a state of near-perfect balance. But the gentle, unrelenting whisper of gravity is always present. It is not a sudden, violent force, but a slow, cumulative persuasion, encouraging the scattered atoms to move just a little closer to one another. Over eons, the densest regions of the cloud begin to contract, pulling in more and more material from their surroundings in a slow, majestic, and unstoppable gravitational collapse. A great, gentle vortex begins to form, a cosmic whirlpool gathering the dust and gas into spinning, collapsing clumps. As these clumps grow more massive, the pressure and temperature at their centers begin to rise. The gravitational energy of the collapse is converted into heat, and a new kind of object begins to glow in the heart of the dark cloud. This is a protostar, an infant sun, not yet a true star, but a prelude to one. It shines not with the fire of nuclear fusion, but with the deep, dusky red light of its own internal heat, a cosmic ember glowing from the sheer force of its own formation. These stellar nurseries are often illuminated in breathtaking colours by the very stars they are creating. In a place like the Great Orion Nebula, the brilliant, hot, and young O and B-type stars at its heart pour out immense amounts of energetic ultraviolet radiation. This radiation ionizes the surrounding hydrogen gas, stripping electrons from the protons, and when the electrons inevitably recombine, they emit light at specific wavelengths, giving the entire nebula a characteristic, beautiful reddish-pink glow. This is an emission nebula, a cloud that sings with its own light. Other nebulae are a ghostly blue, and these are known as reflection nebulae. Here, the starlight is not energetic enough to ionize the gas, but instead, the light simply reflects and scatters off the fine particles of interstellar dust. For the very same reason that our own sky is blue, the dust scatters the shorter blue wavelengths of light more effectively than the longer red wavelengths, creating a soft blue haze around the illuminating stars. These great clouds are the cradles of starlight, the cosmic wombs where the slow and patient dance of gravity transforms cold, dark, and silent gas into the brilliant, life-giving promise of a new sun. Within that glowing, embryonic protostar, the immense pressure of gravity continues its patient work, pulling the sphere of gas ever tighter, causing the temperature and density in its core to rise to levels that are truly beyond our earthly comprehension. The core of the protostar becomes a furnace of such intensity that it is poised on the brink of a final, wondrous transformation, the moment when the true miracle of a star begins. This is the moment when nuclear fusion ignites, a silent, sustained fire that will become the star's heartbeat, a steady pulse of energy that will radiate outwards for billions of years to come. In the crushing environment of the core, where temperatures reach 15 million degrees Celsius, the fundamental forces of nature begin to behave in new ways. The hydrogen nuclei, which are simply individual protons, are stripped of their electrons and are moving at incredible speeds. Normally, their positive electrical charges would cause them to violently repel each other, but in the stellar core, the pressure is so great that this repulsion is overcome, and the protons are forced together. They fuse, creating new, heavier nuclei of helium. In this miraculous process of transformation, a tiny fraction of the original mass of the protons is not needed for the final helium nucleus. This leftover mass does not simply disappear, it is converted into a pure and immense burst of energy, as described by Albert Einstein's famous equation, E=mc². This is the secret of the stars, the source of all their light and heat, a process of creation that turns matter into radiance. For a star the size of our Sun, this process follows a specific and very reliable recipe known as the proton chain, a slow and methodical sequence of fusion reactions that is incredibly efficient at converting hydrogen to helium. This is the star's metabolism, the slow-burning engine that defines its life. And as this engine begins to run, it creates a ferocious outward pressure from the core, a tide of radiation and heat that pushes against the very gravity that created it. This gives rise to the most profound and elegant state of a star's existence, a perfect, delicate balance. The relentless, inward crush of its own gravitational mass is met and precisely countered by the constant, outward pushing force of the energy released by fusion. This state is known as hydrostatic equilibrium, and it is the defining characteristic of a star's long and peaceful life. It is a cosmic stalemate, an exquisite celestial balancing act that holds for billions of years. This equilibrium dictates the star's size, its temperature, and its brightness, keeping it stable and consistent. It is this profound balance that allows a star to shine not as a chaotic, violent explosion, but as a steady, reliable beacon. This long, stable period of adulthood in a star's life is known as the main sequence. Over 90% of all the stars you can see in the night sky, including our own Sun, are currently on the main sequence. They are all in this same, peaceful state of hydrostatic equilibrium, quietly fusing hydrogen into helium in their cores, their internal struggle between gravity and energy, resulting in a serene and constant outward glow. Deep within the silent, unimaginable furnace of a star's core, this invisible engine, this steady heartbeat of fusion, patiently and persistently holds back the weight of an entire world, creating the very light that will one day leave its surface and travel across the void, carrying with it the silent, ancient story of a star's long, balanced, and peaceful life. This long and peaceful life, this perfect billion-year balance between the inward crush of gravity and the outward fire of fusion, is a state of profound stability, but it cannot last forever. For every star, there comes a time when the fuel in its core begins to run low, when its steady heartbeat begins to falter, and the delicate equilibrium is finally and inevitably broken. For the most massive stars in the universe, those giants more than 8 times the mass of our own Sun, this end is not a quiet fading, but a final, defiant, and breathtakingly noble blaze of glory. The story of their demise begins when the star exhausts the primary fuel source it has been burning for millions of years. The hydrogen in its core. With the fusion engine sputtering, the outward pressure weakens, and gravity, the star's lifelong adversary, begins to gain the upper hand. The core contracts and heats up, reaching temperatures so extreme that it can begin to fuse the next element in the sequence, turning the helium ash from the first fire into carbon. This new, hotter fire in the core causes the star's outer layers to expand to an unimaginable size, and the star swells into a red supergiant, a vast, luminous, and bloated object hundreds of times larger than its former self. A star, like Betelgeuse in Orion, is in this very stage, a celestial titan whose outer edges would extend beyond the orbit of Mars if it were in our solar system. Inside the core of this supergiant, a frantic and layered process of creation unfolds. As each fuel source is exhausted, the core contracts further, growing ever hotter and denser, allowing it to fuse progressively heavier elements. A complex, onion-like structure develops deep within the star, with a central core fusing one element, surrounded by a shell fusing a lighter one, and another shell fusing a lighter element still. The star desperately fights against the final victory of gravity, burning through carbon to create neon, then neon to oxygen, oxygen to silicon, and finally, silicon to iron. It is here, with the creation of iron, that the star's fate is sealed. For all the elements leading up to this point, the process of fusion has released energy, creating the pressure needed to hold the star up. But the fusion of iron is different. It consumes energy rather than releasing it. The fire in the core is not just extinguished, it becomes an energy drain. The outward pressure, the star's only defense against its own immense weight, vanishes in an instant. In a fraction of a second, with nothing left to support it, the iron core collapses under its own stupendous gravity. A mass greater than that of our entire sun, which was once a sphere the size of the Earth, implodes to an object no larger than a city, a catastrophic failure of structure that happens at nearly a quarter of the speed of light. This sudden, violent collapse triggers a rebound, a shockwave of unimaginable power that rips back out through the star's outer layers, blasting the entire body of the star apart in a cataclysmic explosion we call a Type II supernova. For a few brief weeks, the light from this single, dying star can outshine its entire home galaxy of 100 billion stars. But this is not merely an act of destruction. In the incredible heat and pressure of the explosion itself, elements heavier than iron are forged for the first time. The silver and gold in our jewelry, the mercury in our thermometers, the uranium that powers our reactors. All of these precious, heavy elements are created in the final, fiery death throes of a massive star. The supernova is the universe's grand act of recycling, a final, generous exhalation that scatters these newly created elements, along with the star's own substance, far and wide into the cosmos, seeding the interstellar clouds with the rich, complex ingredients necessary for the next generation of stars, for new planets, and for the eventual emergence of life itself. The spectacular, expanding cloud of a supernova remnant, rich with the stardust of newly forged elements, is a breathtaking monument to the life and death of a great star. But it is only half of the story. Once the brilliant light of the explosion has faded and the glowing dust has begun to disperse into the interstellar medium, we are invited to turn our gaze back to the very heart of the event, to the point of origin, to witness what remains. For in the center of that celestial graveyard, the collapsed core of the star has survived, transformed by the cataclysm into one of the strangest and most wondrous objects in the universe, a neutron star. This is the remnant left behind by stars that were massive, but not quite massive enough to form a black hole. In the final, crushing moments of the core's collapse, the gravitational pressure was so immense that the very structure of matter was overcome. Protons and electrons in the iron atoms were squeezed together with such force that they merged, forming a single, city-sized sphere composed almost entirely of pure neutrons, packed together as tightly as the universe will allow. The density of a neutron star is so extreme that it defies all earthly comparison. A single teaspoonful, a mere sugar cube's worth of its material, would have a mass of over 100 million tons, weighing more than all of humanity combined. It is an object where the mass of a sun is contained within a sphere that could fit comfortably inside a major metropolitan area. A piece of cosmic matter so compressed that there is no empty space left within its atoms at all. These stellar remnants are not just static, dead cinders. They are often dynamic and energetic objects. Due to a principle known as the conservation of angular momentum, the same principle that causes a spinning ice skater to speed up when they pull their arms in, the slow rotation of the original giant star is magnified immensely as its core collapses. This causes the resulting neutron star to spin at incredible speeds, sometimes hundreds of times per second. Furthermore, the original star's magnetic field is also compressed and amplified to an astonishing degree, creating a magnetic field trillions of times stronger than Earth's. This combination of rapid rotation and a powerful magnetic field can turn the neutron star into a celestial beacon, an object we call a pulsar. The intense magnetic field creates powerful beams of electromagnetic radiation that shoot out from the star's magnetic poles. As the neutron star spins, these beams sweep through space in a steady, repeating pattern, just like the beam of a lighthouse. If one of these beams happens to sweep across our line of sight here on Earth, our radio telescopes detect a precise, repeating pulse of energy. This rhythmic signal, a cosmic heartbeat from the ghost of a dead star, is one of the most regular and predictable phenomena in the universe, with some pulsars keeping time more accurately than our best atomic clocks. Drifting off to the thought of this steady, celestial rhythm, a pulse that has been beating for millions of years, is a profoundly calming meditation. And in the cosmic zoo of extreme objects, there exists a rarer and even more intense variant, the magnetar. This is a special type of neutron star born with a magnetic field that is 1,000 times stronger still, a field so powerful that it defies easy description, a quadrillion times that of our own planet. These objects are a testament to the sheer power that can be locked away in the heart of a stellar corpse, a final, dense, and rhythmic memory of the magnificent, fiery life that came before. This dense, pulsing remnant of a neutron star is the final state for a massive star. But it is not the final, ultimate victory of gravity. For the true titans of the cosmos, those stars born with more than 20 or 25 times the mass of our own sun, there is one last, even more profound chapter to their story. For these giants, when their iron core collapses, the implosion is so overwhelmingly powerful that nothing in the known universe can stop it. The force of gravity is so absolute that it crushes not only atoms, but the very neutrons themselves, smashing through the last line of physical defense. The collapse continues, compressing the heart of the star past the point of no return, down to a single, infinitely dense point, giving birth to the most mysterious and mythologized object in all of creation. A black hole. We often imagine black holes as cosmic vacuum cleaners, aggressively pulling in everything around them, but their true nature is far more subtle and far more peaceful. A black hole's gravity, from a safe distance, is no different from that of the star that came before it. If our sun were to suddenly be replaced by a black hole of the same mass, the Earth would not be sucked in. It would continue in its orbit, undisturbed, though plunged into a sudden and permanent darkness. The true mystery of the black hole lies not in its pull, but in its boundary, a threshold of no return known as the event horizon. This is not a physical surface you could touch, but rather an invisible, spherical border in the very fabric of space-time. It is the point surrounding the black hole where the gravitational pull becomes so strong that the escape velocity exceeds the speed of light. It is a one-way door in the universe. Anything that crosses it, a particle of dust, a wandering asteroid, or a beam of light, can never come back out. You can imagine it as the shore of a silent, one-way river, where the current is flowing at the speed of light itself. To leave, you would have to travel faster than light, a journey that the laws of our universe forbid. This is why a black hole is black. The very light that falls into it cannot escape to tell us what lies within. At the very center of this sphere of darkness lies the theoretical endpoint of the collapse, the singularity. This is a concept that pushes our understanding to its absolute limit, a single point of zero volume and infinite density, where all the mass of the collapsed stellar core is concentrated. It is a place where space and time as we know them are thought to cease to have meaning, where the laws of physics that so elegantly describe our universe seem to break down into a quiet, incomprehensible mystery. And while we cannot see the black hole itself, we can witness its silent, powerful presence through its effect on the light that passes nearby. Its immense mass creates such a deep well in the fabric of space-time that it acts like a cosmic lens. Light from a distant star or galaxy that passes close to the black hole will have its path bent and distorted, a phenomenon known as gravitational lensing. Looking towards a black hole, you would see the background of stars strangely warped, with some stars appearing in multiple places at once, their light tracing a curved path around the invisible object. This is the black hole's shadow, its quiet signature cast upon the cosmos, a visible confirmation of its invisible presence. It is the universe's ultimate expression of stillness, a place of perfect absorption and silence, where the long and ancient journey of a photon finally and peacefully comes to an end. The final, silent rest of a single photon within a black hole marks the end of one stellar story. But the cosmos is a tapestry woven from billions upon billions of such stories, all unfolding together in the grandest structures that matter can form. As we gently pull our focus away from the fate of an individual star, we begin to see the larger communities they inhabit, the vast, spinning, and luminous collections of stars, gas, dust, and dark matter that we call galaxies. These are the great star cities of the universe, immense islands of light adrift in the cosmic ocean, each one a self-contained ecosystem of birth, life, and death, on a scale that transcends human comprehension. And just like cities, galaxies come in a beautiful variety of shapes and sizes, each form telling a different story about its age and its history. Many, like our own Milky Way, are majestic spiral galaxies. They have a bright, central bulge, a dense sphere of older, calmer, often yellowish stars, like a quiet city centre. From this bulge, graceful spiral arms sweep outwards, glittering with the brilliant blue light of hot, young, newly formed stars and glowing with the pinkish haze of the stellar nurseries, where more stars are constantly being born. These arms are the bustling, creative suburbs of the galaxy. Then there are the elliptical galaxies, which appear as vast, smooth, featureless ovals of light. These are the ancient metropolises of the cosmos, composed almost entirely of old, reddish stars, drifting in slow, random orbits. Star formation in these galaxies has long since ceased. The gas and dust have all been used up, and they now exist in a state of quiet, graceful retirement. And finally, there are the irregular galaxies, those with no defined shape at all, often appearing as beautiful chaotic splashes of light. These are typically the result of galactic collisions, a temporary state of disruption where the gravitational dance of two galaxies merging has thrown their stars into a disordered, but often stunningly beautiful, arrangement. The sheer scale of these star cities is difficult to internalize. A typical galaxy, whether spiral or elliptical, will contain somewhere between 100 billion and a trillion stars. If you were to try and count to just 100 billion, at a rate of one number per second, without ever stopping to eat or sleep, it would take you over 3,000 years. And this is just one galaxy, among hundreds of billions, and perhaps trillions, of others scattered throughout the observable universe. Yet, the most astounding fact about these galaxies is that the brilliant light of all those stars is not the whole story. When astronomers measure how fast galaxies rotate, they find that the stars on the outer edges are moving far too quickly. According to our understanding of gravity, the visible matter, the stars, gas, and dust, is not nearly massive enough to hold on to these speeding outer stars. The galaxies should be flying apart. The only way they can remain bound together is if they are embedded in a vast, invisible halo of some other kind of substance, a mysterious, unseen mass that we call dark matter. This is not just a small correction. It is believed that dark matter makes up about 27% of the mass energy of the universe, while all the normal matter that we can see and touch accounts for less than 5%. Dark matter is the invisible scaffolding of the cosmos, the silent, gravitational glue that holds the star cities together, giving them their structure and their very existence. And these great structures are not static. They are in constant, slow motion, drifting, dancing, and sometimes merging. When two galaxies collide, it is not a violent crash, but a slow and graceful intermingling over hundreds of millions of years. Because the space between stars is so vast, individual stars rarely, if ever, hit each other. Instead, the two galaxies pass through one another like ghosts, their gravitational fields tangling, stripping away streams of stars and gas, and often triggering a brilliant burst of new star formation as their interstellar clouds are compressed. A final, beautiful dance that ends with them settling into a single, larger galaxy, ready to continue their long and silent cosmic story. These great star cities, these immense and ancient island universes, can feel distant and impersonal, but there is one that is not an object to be viewed, but a home to be inhabited. We are living inside of one right now. It is our galaxy, the Milky Way. On a clear, dark night, far from the lights of any city, you can see it as our ancestors did. A faint, luminous, and ethereal river of light stretching from horizon to horizon. A soft, cloudy band that the ancient Greeks imagined as a stream of divine milk. For millennia, its true nature was a mystery, but we now understand that this beautiful, hazy arc is the light of billions of unresolved stars, the view from within the flat, spinning disk of our home galaxy. We are not looking at an object in the sky. We are looking through the densest part of our own cosmic neighborhood towards its brilliant, crowded center. To truly picture our place within it, you must imagine the Milky Way as a vast, barred, spiral galaxy, a spinning celestial pinwheel of immense proportions. At its heart is a dense, bright, elongated bar of old, yellowish stars, which is itself embedded in a larger, spherical central bulge. From this core, several major and minor spiral arms sweep gracefully outwards, glittering with the light of over 200 billion stars. This entire, flat disk, over 100,000 light-years across, is itself embedded in a vast, spherical, and mostly invisible halo of dark matter, ancient stars, and globular clusters. Our Sun, and our tiny planetary system with it, does not reside in the chaotic, high-radiation environment of the galactic core, nor is it cast out into the lonely, sparse fringes of the galaxy. Instead, we find ourselves in a rather peaceful and quiet cosmic suburb, nestled within a minor arm called the Orion Cygnus Arm, or simply the Orion Spur. Our position is about 27,000 light-years from the galactic center, a fortunate placement that has perhaps sheltered our world from the frequent supernova explosions and intense radiation that characterize the more crowded regions of the galaxy. It is from this serene vantage point that we look inwards and outwards, our view shaping the beautiful band of light we see. At the very heart of this grand, spinning structure, the gravitational anchor around which our entire galaxy revolves, lies a quiet and sleeping giant. This is Sagittarius A star, the supermassive black hole that resides in the Milky Way's core. Though it is an object of immense power, with a mass equivalent to about 4 million of our suns, it is currently in a very dormant state, only occasionally sipping on small amounts of interstellar gas. It is not a monster waiting to consume the galaxy, but rather the calm, silent center of our collective gravitational dance. And this dance is a slow and majestic one. Just as the Earth orbits the Sun, our entire solar system is also in a vast, slow orbit around the center of the Milky Way. The time it takes for us to complete one full circuit, one galactic year, is approximately 230 million years. This is a timescale so vast it dwarfs the entire history of the human species. The last time our solar system was in this same physical location in its orbit around the galaxy, the very first dinosaurs were just beginning to evolve and walk upon the Earth. Since its formation, our planet has made this grand circuit only about 20 times. This slow, silent journey is the fundamental rhythm of our existence on a cosmic scale, a reminder that we are not just inhabitants of a planet, but passengers on a star system, perpetually sailing through the luminous, star-dusted river of our galactic home. This feeling of being a passenger on a great, stellar river, of belonging to our home galaxy, the Milky Way, naturally brings a sense of place and context. But the story of our cosmic address does not end there. For our galaxy, as vast and self-contained as it seems, is not an isolated island adrift in an endless, uniform void. It too is a part of something larger, a participant in a pattern of such breathtaking scale and unexpected elegance that it has only been revealed to us in the last few decades of astronomical observation. This is the cosmic web, the largest known structure in the entire universe. As we zoom out far beyond the scale of a single galaxy, we discover that galaxies are not scattered randomly through space, like dust motes in a sunbeam. Instead, they are arranged in an intricate and delicate network, a vast, interconnected filamentary structure that pervades the entire cosmos. Imagine a vast, three-dimensional spider's web, and on this web, the galaxies are like tiny, glittering dewdrops, clinging to the luminous strands. These strands are the great filaments of the universe, unimaginably long, thin chains of galaxies and dark matter that can stretch for hundreds of millions of light-years across the void. Where these shimmering filaments cross and intersect, the galaxies cluster together in dense, bright nodes. These are the great galaxy clusters and superclusters, the bustling intersections of the cosmic web, where hundreds or even thousands of galaxies are bound together by their immense, mutual gravitational pull. And between the filaments and clusters of this grand cosmic network lie the great voids. These are the vast, dark, and profoundly empty regions of the universe, immense bubbles of near-nothingness that the web seems to surround. They can be hundreds of millions of light-years in diameter, and they are places of a deep and humbling silence, containing very few, if any, galaxies. It is the beautiful, stark contrast between the bright, galaxy-rich filaments and the dark, empty voids that gives the cosmic web its delicate, cellular, and almost organic appearance. This structure is so reminiscent of biological patterns, like the neural networks in a brain or the veins of a leaf, that it suggests a profound and underlying order to the universe on the very largest of scales. And this beautiful structure did not arise by chance. It is the visible manifestation of the invisible architecture of the cosmos, a blueprint drawn by dark matter in the earliest moments of the universe. In the aftermath of the Big Bang, the mysterious, unseen dark matter, which outweighs normal matter by more than 5-1, began to collapse under its own gravity, forming a vast, underlying web-like scaffolding. Over hundreds of millions of years, the normal, visible matter, the hydrogen and helium gas that would eventually form stars and galaxies, felt the gravitational pull of this pre-existing dark matter structure. The gas was drawn into the densest parts of the web, flowing along the filaments like rivers and pooling in the deep gravitational wells of the nodes. It was here, within this invisible framework, that the gas condensed and the first stars and galaxies ignited, lighting up the cosmic web from within and revealing its hidden structure to our telescopes. The luminous universe of galaxies that we see is merely the beautiful embroidery on an immense and invisible tapestry of dark matter. This vision of the cosmos as a single, interconnected whole is a profoundly peaceful one. It tells us that nothing is truly alone, that every star, every galaxy, is a part of a coherent, universal pattern, a single, vast, and silent story of structure and connection. This breathtaking vision of the cosmic web, this understanding that our galaxy is but one glittering dewdrop on a single strand of a universal tapestry, gives us a profound sense of our place in the cosmos as it exists today. But it also invites our minds to drift even further back, beyond the birth of galaxies, beyond the formation of the very first stars, to a time before any of this grand structure existed. We are drawn to ask, what did the universe look like in its infancy, at the very beginning of its long and silent story? To find the answer, we must listen for the oldest, faintest, and most profound echo in all of creation. The cosmic microwave background. This is the first light of the universe. A faint, pervasive afterglow from the dawn of time itself. For the first 380,000 years after the Big Bang, the universe was an unimaginably hot, dense, and chaotic place. It was not dark, but it was completely opaque, a swirling, uniform fog of primordial plasma, a sea of protons, neutrons, and electrons unbound by the familiar rules of atomic structure. In this incandescent fog, photons, the particles of light, could not travel freely. They were trapped in a cosmic pinball game, constantly scattering off the free-roaming electrons, unable to travel more than a few millimeters without being deflected. It was a universe filled with light, but a universe where light had no freedom, no voice, and no ability to carry a message. But as the universe expanded, it also cooled, and when it reached the age of about 380,000 years, it crossed a critical temperature threshold. It became cool enough for the protons and electrons to finally combine, binding together to form the first stable neutral atoms of hydrogen. This event, known to science as recombination, fundamentally and forever changed the nature of the cosmos. In a remarkably short period of time, the opaque fog of plasma cleared, and the universe became transparent for the very first time. The photons that existed at that precise moment were suddenly liberated. With the electrons now safely bound within atoms, the light particles were free to travel in straight, unimpeded lines across the cosmos, to begin a journey that has continued for the last 13.8 billion years. The cosmic microwave background is that very light. It is a snapshot, a baby picture of the universe at the exact moment it became transparent. And today, this ancient light is all around us. It is no longer searingly hot. The vast expansion of the universe has stretched its wavelengths, redshifting it from a brilliant, visible glow all the way down to the low-energy microwave portion of the electromagnetic spectrum. It now has a faint and incredibly uniform temperature of just 2.73 Kelvin, which is about minus 270.42 degrees Celsius, only a few degrees above the theoretical cold of absolute zero. It is a silent, cold, and invisible hum of energy that fills every cubic centimeter of space, coming at us from every direction in the sky with almost perfect uniformity. It is the oldest and most distant thing we can ever hope to see. Yet, the most important part of its story lies not in its uniformity, but in its almost imperceptible imperfections. When we map this ancient light with incredibly sensitive instruments, we find that it is not perfectly smooth. There are minuscule temperature fluctuations, tiny ripples, infinitesimally small variations in density from one spot to another, differences of only about 1 part in 100,000. These tiny, warmer, and cooler spots in the baby picture of the universe were the seeds of everything that was to come. The slightly denser, slightly cooler spots were the regions with just a tiny bit more gravitational pull, and over the next billion years, these seeds would slowly and patiently grow, attracting more and more matter, to eventually become the great clusters and superclusters of galaxies that form the cosmic web today. This ancient, silent light is not just an echo of the past, it is the very blueprint of our cosmic home. That ancient light, that blueprint from the dawn of time, tells the story of how cosmic structure began, but it also speaks of a universe that was, in its beginning, chemically very simple. The Big Bang forged the rawest of materials: hydrogen, the lightest element, and helium, the second lightest, and almost nothing else. This primordial universe had no carbon, no oxygen, no iron, none of the complex and beautiful chemistry that makes our world, and our own bodies, possible. This, then, leads to the most intimate and personal connection we have to the stars. The story of where these other, heavier elements came from is the story of us. It is the profound and literal truth that we are made of stardust. Every other element on the periodic table, every atom that is not hydrogen or helium, was forged in the heart of a star that lived and died long before our sun was ever born. The carbon atoms that form the backbone of our DNA, the oxygen atoms we breathe to give us life, the calcium in our bones, and the iron in our blood that carries that oxygen to our cells. Every single one of these vital atoms was created through the patient alchemy of nuclear fusion inside a stellar core, or in the final, fiery cataclysm of a supernova explosion. The universe, in its great, slow wisdom, has spent billions of years patiently enriching itself, transforming the simple gas of its birth into a complex and life-giving chemistry. The first generation of stars were giants, formed from pure hydrogen and helium, and they lived fast and died young, exploding as supernovae and scattering the first batches of carbon, oxygen, and other new elements into the interstellar clouds. The next generation of stars formed from these newly enriched clouds, and in their cores they forged even heavier elements, and they too, in their time, gave these creations back to the galaxy. It is a grand and perpetual cycle of cosmic recycling, of life, death, and rebirth on a galactic scale, with each generation of stars seeding the future with greater and greater chemical possibility. Our own solar system is a direct beneficiary of this ancient lineage. We are the children of countless generations of ancestral stars. The nebula from which our sun and its planets formed about 4.6 billion years ago was a rich inheritance, a cloud already laden with the heavy element, dust from thousands of supernova explosions that had occurred over the vast history of the Milky Way. The very ground beneath your feet, the silicon in the rocks, and the iron at the Earth's core, is all the recycled ash of long-dead suns. Now, take a slow, deep breath and consider for a moment a single atom of iron in the hemoglobin of your blood. The journey that atom has taken to be with you right now is perhaps the most epic story one could ever tell. It was born billions of years ago in the core of a massive star, in a crucible of unimaginable temperature and pressure. For millions of years it was part of that star's life, until the star reached its end and exploded, casting that iron atom out into the cold, dark void of space at incredible speed. For perhaps 1 billion years, it drifted through the interstellar medium, part of a great, swirling cloud of gas and dust. Eventually, it was drawn by gravity into a new, collapsing nebula, the very one that would become our home. It became part of the spinning protoplanetary disk and was incorporated into the molten rock of the nascent Earth. For billions of years more, it cycled through the planet's crust and mantle until it was eventually weathered into the soil, absorbed by a plant, eaten by an animal, and finally found its way into your body, where it now performs the sacred task of carrying the breath of life through your veins. You are not separate from the universe. You are a direct and living continuation of its creative, cosmic story. Your body is an archive of the lives and deaths of stars, a testament that the cosmos is not something you just look at, but something you are. This profound and intimate realization that our bodies are living archives of stellar history naturally expands the heart and the mind outwards. If the very elements of life, the carbon, the nitrogen, the oxygen, were forged in the hearts of stars and scattered like seeds throughout the cosmos, then it is a quiet and logical next step to wonder if perhaps our world is not the only garden where these seeds have taken root. This thought, once the sole domain of philosophers and poets, has now become a gentle and patient branch of scientific inquiry, as we have discovered that our sun is not unique in its hosting of a planetary family. For nearly all of human history, the 8 planets of our solar system were the only ones we knew. But in just the last few decades, our view of the cosmos has been fundamentally transformed by the discovery of thousands of exoplanets, worlds orbiting other suns. Each one is a new point of light on our cosmic map, a testament to the fact that planets are not a rare exception, but a common and natural outcome of the process of star formation. Finding these distant worlds is an act of incredible subtlety and precision. The most common method we use is called the transit method, which requires a kind of cosmic alignment and immense patience. We stare, unblinking, at a single star for years at a time, measuring its brightness with exquisite accuracy. If that star happens to have a planet whose orbit is perfectly aligned with our line of sight, then once per orbit, the planet will pass directly in front of the star, causing a tiny, almost imperceptible dip in the star's light. It is a minuscule shadow, a temporary dimming that might last for only a few hours, like watching for a single moth to fly in front of a brilliant, distant searchlight. By watching for this tiny, repeating wink, we can not only confirm a planet's existence, but also learn its size and the length of its year. Another elegant method is to listen for a tiny wobble in the star's light, a technique called the radial velocity method. A large planet, like Jupiter in our own solar system, exerts a noticeable gravitational tug on its parent star, causing the star to dance in a small, tight circle as the planet orbits it. This tiny motion, this stellar wobble, can be detected from hundreds of light years away by looking for a subtle, periodic shift in the star's light. As the star wobbles towards us, its light is slightly compressed, shifting towards the blue end of the spectrum, and as it wobbles away, its light is stretched, shifting towards the red. We are not seeing the planet itself, but rather detecting the star's silent dance with its unseen companion. With thousands of such worlds now catalogued, the search has gently shifted from mere discovery to a quiet characterization, a search for worlds that might be like our own. This has given rise to the concept of the habitable zone, sometimes known as the Goldilocks zone. This is the orbital region around any given star that is just right for life as we know it, not so close that the star's heat would boil away any liquid water, and not so far that any water would be permanently frozen as ice. It is the gentle, temperate band where it is possible for liquid water, the essential solvent for life on Earth, to exist on a planet's surface. And as we find more and more of these worlds, we are humbled by the sheer diversity of what the universe can create. We have found hot Jupiters, gas giants larger than our own, orbiting their stars in a matter of days. We have discovered super-Earths, rocky worlds that are far more massive than our own. We have seen planetary systems with orbits and arrangements that seem to defy our models of how solar systems should form. The universe, it seems, is far more imaginative in its creations than we have been in our predictions. Each new exoplanet we discover is another quiet possibility hanging in the velvet darkness. Another potential setting for a story we do not yet know, a gentle reminder that the cosmos may be filled with more wonders and perhaps more homes than we have ever dared to dream. This gentle, unfolding dream of countless other worlds, this quiet census of Goldilocks planets and distant solar systems, fills the mind with a sense of wonder and boundless possibility. The ingredients for life are everywhere. The potential homes for life seem to be common. And our universe is ancient, with billions of years of history preceding our own existence. Plenty of time for other stories to have begun. And so, as we turn our radio telescopes to the sky and listen, we are greeted by the most profound and humbling mystery of all, a great, deep, and unnervingly perfect silence. This contradiction between the high expectation of life and the stark, observational reality of its apparent absence is known as the Fermi paradox, first articulated in a simple, casual question by the physicist Enrico Fermi: where is everybody? It is a thought that is both simple and deeply unsettling. If the galaxy is filled with billions of Earth-like worlds, and many of them are billions of years older than our own, then it seems that at least one civilization should have had more than enough time to develop interstellar travel and leave its mark on the galaxy in some way that we could detect. Yet, the sky is quiet. To give this question a more formal structure, astronomers have developed the Drake equation. It is not an equation in the traditional sense, but rather a chain of probabilities, a way to organize our thinking and our ignorance. It asks us to consider the rate of star formation, then multiply that by the fraction of stars that have planets, then the fraction of those planets that are habitable, then the fraction on which life actually arises, then the fraction of that life which becomes intelligent, then the fraction of intelligent life that develops detectable technology. And finally, it asks how long such a technological civilization might last. While we are beginning to have good estimates for the first few terms in this chain, the latter terms remain a complete and utter mystery. The equation becomes a mirror, reflecting back at us the limits of our own knowledge. And so, we are left to wonder about the possible reasons for the silence. Perhaps there is a great filter, a step in the evolution of life or civilization that is so incredibly difficult and improbable that almost no one ever makes it through. Maybe the filter is behind us. Perhaps the initial leap from non-living chemistry to the first living cell is the near impossible miracle, and we are one of the very first to have won this cosmic lottery. Or perhaps the filter lies ahead of us, a sobering thought that technological civilizations almost inevitably discover a way to destroy themselves before they can ever reach the stars. Other, gentler possibilities exist. Perhaps the galaxy is teeming with life, but it is mostly simple, microbial life, and the jump to complex, intelligent creatures is the rare event. Or perhaps intelligent civilizations are common, but they have no desire to shout their existence across the cosmos, choosing instead to live quietly, to explore their own inner worlds, or to communicate in ways we cannot yet comprehend. But perhaps the silence is not a problem to be solved, but a message to be understood. Perhaps the great quiet of the universe is an invitation for us to listen more intently to the one place we know that is not silent, the one world we know that is singing with a vibrant and complex chorus of life. The silence of the stars can make the sound of the wind through the trees, the rhythm of the waves on the shore, or the simple act of a deep and peaceful breath feel like the most precious and sacred things in the entire cosmos. The Fermi paradox may be the universe's way of whispering a gentle reminder of just how rare, how beautiful, and how worthy of our care our own noisy, luminous, and living world truly is. This great cosmic silence, this quiet backdrop against which we can appreciate the vibrant sound of our own world, also invites us to contemplate the nature of time. Our existence, both as individuals and as a species, is brief and luminous, a fleeting moment of warmth and noise in a universe that is mostly cold and quiet. And as we cast our minds forward, far into the deep future, we come to understand that this brief, luminous quality applies not just to us, but to the stars themselves, and eventually to the entire cosmos as we know it. The story of the universe's end is not a tale of a sudden, fiery apocalypse, but a slow, gentle, and profoundly peaceful fading into a final and eternal twilight. Our own sun will be one of the earlier participants in this long goodbye. In about 5 billion years, it will exhaust the hydrogen fuel in its core. Its center will contract and heat up, while its outer layers will expand, transforming it into a red giant that will swell to engulf Mercury, Venus, and possibly even the Earth. After this final, brilliant phase, it will shed its outer atmosphere as a beautiful planetary nebula, and its core will remain behind as a small, dense, and intensely hot white dwarf. This stellar remnant will have no internal fire. It will simply be a cooling ember, spending the next trillion years or more slowly radiating away its residual heat, eventually fading into a cold, dark, and invisible object known as a black dwarf. This is the eventual fate of most stars in the universe. And so, the era we are currently living in, the time of brilliant, star-filled galaxies, is a temporary one. Astronomers call it the stelliferous era, the star-bearing age. It is the vibrant, energetic, and creative youth of the cosmos, a time when new stars are still being born from nebulae, and the night sky is filled with their light. But it will not last forever. Trillions of years from now, long after the last star like our sun has faded, the very last stars to be born, the tiny, dim, and incredibly long-lived red dwarfs, will finally flicker and die. The raw material for star formation will be exhausted, and the universe will enter a new and profoundly different age. The degenerate era. This will be a universe of ghosts and embers. The only objects remaining will be the cold, dead remnants of stars. Black dwarfs, neutron stars, and black holes, all drifting silently through an expanding and ever-darkening cosmos. The galaxies we know will have dissolved, their stellar corpses slowly being ejected into the intergalactic void by ancient, chaotic gravitational interactions. It will be a universe of profound and almost perfect darkness, a silent realm of cosmic relics. But even this is not the final end. Over timescales that are so vast they beg a description, trillions upon trillions of years and more, even these degenerate remnants will begin to decay. Quantum mechanics suggests that protons themselves may be unstable, and over eons, the black dwarfs and neutron stars may slowly evaporate into radiation. The last holdouts will be the supermassive black holes at the centers of long-dead galaxies, and they too will eventually succumb, slowly leaking away their mass and energy through a process known as Hawking radiation until they too have vanished into a final, faint puff of light. All the while, the universe will continue to expand, and this expansion, combined with the decay of all matter, will lead to the theoretical final state of the cosmos, the heat death. This is not an event, but a final condition, a state of maximum entropy. It is a universe where all the energy has spread out so evenly that no temperature differences remain. Everything will be at a uniform, constant temperature, just a fraction of a degree above absolute zero. There will be no more available energy to fuel any process, to form any structure, or to sustain any thought. It will be a universe in a state of perfect, eternal, and unchanging equilibrium. A final, gentle, cosmic exhalation into a quiet that will never again be broken. Contemplating this ultimate end is not a cause for fear, but a reason for a deep and profound appreciation of the here and now, a recognition that the brilliant, complex, and light-filled universe we inhabit is a precious and fleeting gift. This precious, fleeting gift of a light-filled universe, this brief warmth in an eternity of cold, brings our long journey through time and space back to its gentle and final destination. This present moment, with you, resting quietly in the soft darkness. We have drifted from the intimate act of a single photon striking your eye to the life and death of our sun, through the cradles of creation and the ghosts of dead stars. We have journeyed through our home galaxy, the Milky Way, witnessed its place in the grand cosmic web, and listened to the first, faint whisper of light from the dawn of time itself. We have felt the profound truth of our own stardust bodies, imagined the countless possible worlds around other suns, and sat with the great, humbling silence of the cosmos. And now, at the end of this journey, we find the final and most wondrous fact of all, the existence of a consciousness that is able to perceive it. There is a quiet, philosophical idea which suggests that the universe we observe must, by its very nature, be one that is capable of giving rise to observers. The laws of physics, the values of the fundamental constants, the very structure of the cosmos, all seem to be exquisitely fine-tuned for the emergence of complexity, for stars, for planets, and for life. This suggests a beautiful and unbreakable link between our own conscious existence and the grand reality we inhabit. We are not an accident or an afterthought, but a meaningful and perhaps even necessary part of the cosmic story. The very act of scientific inquiry, of looking up at the sky and asking questions, is a profound expression of this connection. It is the universe itself, through us, becoming aware of its own majesty, its own beauty, and its own deep, silent history. The stories we tell, whether through the mathematics of physics or the poetry of myth, are our way of reaching out, of trying to understand our place in the grand, unfolding narrative. And this act of reaching, of contemplating the immense and the awesome, has a gentle and healing effect on the human mind. The feeling of awe, so often inspired by the starry night sky, has been shown to have a real and measurable power to soothe our anxieties. It places our personal worries and daily struggles into a much larger perspective, reminding us that we are part of something vast, ancient, and enduring. It fosters a sense of connection, not just to the cosmos, but to each other, as fellow travelers on this small, blue world. Your journey tonight, listening to these quiet words, has been more than just a passive learning. It has been an active participation in this ancient human tradition of finding peace and perspective in the stars. The final truth is a simple one. The ancient light from 1 billion distant suns travels for eons across the silent void, and it finds its ultimate purpose and its final meaning not in the emptiness, but in the quiet, conscious mind that receives it. You are not just a spectator of the universe. You are the place where the universe arrives. You are the universe's awareness. And in that realization, there is a deep and abiding peace. You belong here. You are home. Thank you so much for joining me on this journey through the ancient light of the stars. I hope it has brought you a measure of peace and comfort. I would love to read in the comments which part of our journey resonated most deeply with you as you drifted towards sleep. If you have found solace here, please do consider leaving a like and subscribing to the channel for more gentle stories for sleep. Your support means the world to me. For now, there is nothing left to do but to let go, to allow your mind to be as quiet and as vast as the night sky itself. Sleep well.